chemists, we like to calculate and count stuff. And what we absolutely prefer to count is, of course, atoms. But how do you count atoms? I mean, they're so small. Well, naturally, we have a few tricks up our sleeve. And these tricks are the physical quantities called amount of substance, molar mass, and mass. Let's start by looking at how much a single molecule weighs. Oh, and by the way, bring out your calculator too, because you'll need it to keep up with all the calculations that I do in this video. So, take this to your notes. What's the mass of one molecule of H2, hydrogen gas? To calculate that, we take a peek at the periodic table. Hydrogen is up here to the left, and if we enlarge it a little bit, we can see that the atomic mass for hydrogen is 1.008 U. Let's write that down too. A hydrogen molecule, however, consists of two hydrogen atoms. That's why it's written H2. Thus, we multiply by 2 and we see that a hydrogen molecule weighs 2.016 U. So, now we know what the mass of one hydrogen molecule is. But now, let's calculate how much 6.022 times 10 to the 23 hydrogen molecules weigh. A peculiar number perhaps, but soon you'll understand why I chose it. Anyway, we write that 1 U corresponds to 1.6605 times 10 to the minus 24 grams. We know that a single hydrogen molecule weighs 2.016 U, and with the help of this conversion factor, we can calculate how many grams that is. Since 1 U corresponds to 1.6605 times 10 to the minus 24 grams, we can multiply 2.106 U with 1.6605 times 10 to the minus 24 grams per U and calculate that one single tiny hydrogen molecule weighs 3.347568 times 10 to the minus 24 grams. But don't take my word for it. Do the calculations on your own calculator so you learn how to do these kinds of calculations. Now we know the mass of a single hydrogen molecule, but I want to know the mass of 6.022 times 10 to the 23 molecules. We multiply by 6.022 times 10 to the 23 and get that they weigh 2.015905545 grams, approximately 2.016 grams. Can you see what's peculiar here? A single hydrogen molecule weighs 2.016 U, while 6.022 times 10 to the 23 molecules weigh 2.016 grams. We have the same figure, but different units. This is the cunning trick I was talking about. Let's explore that further. Now we make a small table again, and in the header you write that one molecule weighs and that 6.022 times 10 to the 23 molecules weigh in this way. And we fill in that one H2 molecule weighs 2.016 U, while 6.022 times 10 to the 23 H2 molecules weigh 2.016 grams. Let's look at another example, this time how much a single oxygen molecule weighs. We look at the periodic table again and enlarge it a little bit and see that one oxygen atom weighs 16.00 U. We write that in our notes too. An oxygen molecule, though, consists of two oxygen atoms. It's O2, remember? So we rapidly calculate that one oxygen molecule weighs 2 times 16.00 U equals 32.00 U. Okay? Now, let's look at, that's right, the mass of 6.022 times 10 to the 23 oxygen molecules. As I said before, 1 U corresponds to 1.6605 times 10 to the minus 24 grams. This means that one oxygen molecule, which weighs 32.00 U, also weighs 5.3136 times 10 to the minus 23 grams. And once again, don't trust me. Do the calculations on your own calculator too. 6.022 times 10 to the 23 oxygen molecules weigh a little bit more. 6.022 times 10 to the 23 times more, to be exact. According to my calculations, they weigh 31.9984992 grams. That is approximately 32.00 grams. And isn't this exciting? Once again, the same number appears. One single oxygen molecule weighs 32.00 U, while 6.022 times 10 to the 23 oxygen molecules weigh 32.00 grams. Make sure you put that number in your table too. One molecule has a mass of 32.00 U, while 6.022 times 10 to the 23 oxygen molecules has a mass of 32.00 grams. Now, can you see that this number, 6.022 times 10 to the 23, it's a real beauty. That number is so special, it's got its own term. 6.022 times 10 to the 23 is called a mole. Mole, that's like a word of quantity. There are lots of other words of quantities in English. For example, a pair or a couple, which is 2 pieces. A dozen, which is 12 pieces. A score is 20. You know, like in 7 years ago. A gross is 12 dozens, which equals to 144. A grand is 1,000 pieces. A myriad is 10,000. And then finally, a mole is 6.022 times 10 to the 23 pieces. And it doesn't matter what it is that you're counting. The amount in a mole is always the same, just like a pair is always 2 and a dozen is always 12, whether it's eggs or donuts. If you have a mole of carbon atoms, they are just as many as a mole of elephants or a mole of television sets, 6.022 times 10 to the 23. So, how do you use the number 6.022 times 10 to the 23? Well, you can view it as a kind of conversion factor from atomic mass units to grams. The number 6.022 times 10 to the 23 is called Avogadro's constant, or sometimes Avogadro's number. We write it Na, and its unit is 1 per mole. Also note that the N is in italics and the A is subscripted. That's how it's usually written. We write Avogadro's constant like this. Na equals 6.022 times 10 to the 23 per mole. Now we move on to the amount of substance. The amount of substance answers the question, how many moles do we have? It's written N, note that it's in italics too, and has the unit mole. For example, we can write that N equals 25 mole. That's just an arbitrary example. But we'll try some calculations in this too. Let's say a piece of iron consists of 2.5 mole iron atoms. How many iron atoms is that? We write like this, and leave some space above here, that we have 2.5 mole. In each mole, there is 6.022 times 10 to the 23 atoms, so we multiply by 6.022 times 10 to the 23 per mole, like this. And then we see that there are 1.5055 times 10 to the 24 atoms, or approximately 1.5 times 10 to the 24 atoms in 2.5 moles of iron. But let's also write what we've done here nicely and mathematically. The amount of something, we often write this with a capital italic N. I also add Fe in subscript here to show that now we're calculating the number of iron atoms. And what we did was actually multiplying the amount of substance, 2.5 mole, with Avogadro's constant, 6.022 times 10 to the 23 per mole. And mole divided by mole, they cancel out. So we get no unit at all here, just a number, the number of atoms. Here's another example. A piece of gold that I have in my lab contains 6.1 times 10 to the 21 atoms. What's the amount of gold in this case? Now, when we calculate the amount of gold, we write N directly, with AU nicely subscripted like this. We want to know how many times 6.022 times 10 to the 23 goes into 6.1 times 10 to the 21. This means we have to divide the number of gold atoms, NAU, by Avogadro's constant, Na. Let's just write the numbers like this. 6.1 times 10 to the 21 over 6.022 times 10 to the 23 per mole. I punch it into my calculator, try it, you too, and arrive at 0.0101295 mole, which is approximately 10 times 10 to the minus 3 mole. Note the unit here. Since we divide by 1 per mole here, the unit in the answer becomes mole. The amount of substance is intimately linked to the molar mass. We already know that 1 mole of something is 6.022 times 10 to the 23 pieces. Molar mass tells us how much a mole of something weighs. The molar mass is written with an italic M in this way and has the unit grams per mole. Let's calculate the molar mass of hydrogen gas. First, we'll do it in a complicated way, and then I'll show you a shrewd shortcut. To calculate the molar mass of hydrogen gas, we need to find the mass for a single hydrogen molecule and then multiply it with Avogadro's constant. We know, since earlier in this video, that the mass of a single hydrogen molecule is 2.016 U, which corresponds to 3.347568 times 10 to the minus 24 grams. So, let's multiply that with Avogadro's constant, 6.022 times 10 to the 23 per mole. When I do that on my calculator, I get that the molar mass equals 2.016 grams per mole. And here comes the really clever bit that I've been talking about. This is the same figure as the molecular mass right here. This means that when I check in my periodic table, I can always see that the atomic mass for an atom, for example hydrogen, is 1.008 U. But at the same time, this means that its molar mass is 1.008 grams per mole. This is something that we'll use shortly to count atoms. But first, this leads to an important mathematical relation. The molar mass tells us how much a mole of something weighs. That's why we can write like this. The molar mass is equal to the mass divided by the amount of substance. If we write it as a proper mathematical relation, it looks like this. The molar mass M is equal to the mass M divided by the amount of substance N. Just to be sure, we write that M is the molar mass in grams per mole, M is the mass in gram, and N is the amount of substance in mole. Let's finish with a calculation on that. I ask the question, how large is the amount of substance in 36.0 grams of water? In order to calculate that, we take advantage of our little relation M equals M divided by N. We want to calculate the amount of substance N. To do that, we want N by itself on one side of the equal sign. We can get that if we first multiply by N on both sides of the equal sign, like this. Now we can lose N on the right side and we instead get this expression. But N is still not by itself. We can, however, fix that by dividing by the molar mass M on both sides, like this. Now we can get rid of M on the left-hand side and we arrive at N equals M over M. Now, what was it that we were supposed to calculate? That's right, it was the amount of substance of water, NH2O. The mass of the water, we know that from the question, it is 36.0 grams. But what is the molar mass of water? Well, we can calculate that with the help of the atomic masses in the periodic table. Here I can see that the molar mass of hydrogen is 1.008 grams per mole, and then there are 2 hydrogen atoms in each water molecule, and that the molar mass of oxygen is 16.00 grams per mole. So let's write that down too. The molar mass of water is 1.008 gram per mole times 2 plus 16.00 grams per mole, which is equal to 18.016 grams per mole. We plug in these values into our relation and find that the amount of substance water is 36.0 grams divided by 18.016 gram per mole, which is approximately equal to 2.00 moles. Once again, Note how I do the unit conversion here. Gram divided by gram here, it is 1 and therefore we can get rid of them. And when you divide by 1 per mole here, only mole is left. So, in 36.0 grams of water, there is 2.00 mole. Now, if you are completely confuzzled, don't worry. The concept of moles and amount of substance is always a little bit difficult in the beginning. But trust me, we'll use it so many times in the future of this course that eventually you'll be very familiar with it.